several postdocs, and we go here to give a seminar of his recent work.
Okay, thanks, Lorenz. So the title of the seminar is Proving Topological Phase Transitions by Non-Markovianity. The work was done in collaboration with Roberta, with Albert, and with Stefano Longhi, who came to visit us a few months ago. Actually, we started the project when Stefano came here, because he was the expert in these topological phases of matter. We didn't know anything about it before he came here. So the aim of this work is to bring together two, let's say, quite different communities. On the one side, there is the problem of characterizing topological phases of matter, systems that are not matched to each other by continuous transformation are called topological, because you have to close some gap, for instance, to go from a donut to a bread, you have to close the hole inside, you have to change phase. And so if you want to speak about physics, you can think about bands in conductors, in insulators, when the way different bands are connected can define topology in analogy to this kind of discontinuity. And on the other hand, we have the physics of open quantum systems. You have a small system, an atom, a two-level system, and a small harmonic oscillator that is immersed into a bigger quantum system that actually acts as a thermal environment. Depending on the strength of the interaction, on the shape of the bath, of the shape of the small system, if you study the dynamics of the small unit, you can have possible memory effects. You can have a dynamics of the small unit that has this shape or this shape. This is just qualitative. I will explain this afterwards. Let's say that depending on something, you can have either this behavior or this one. If I want to make a picture summary of my presentation, is this one. You have two different phases. One is a bread, another one is a donut. What? A pretzel, sorry. They act like a big quantum environment, and they connect them to a small quantum unit, external, and as a result, you hope to find something like this. If there is a topology here, you find something like this. If there is another topology, you find something like this. So this is our goal, to find something that can be characterized this way. Actually, this is very generic. We specialized on a model, on a simple model, actually on the simplest model that admits topological phase transition. It's called Su-Schrieffer-Heeger, and was introduced, let's say, 40 years ago to describe a chain of molecules that compose the polyacetylene. And as I said, it's the simplest model presenting a topological phase transition, and can be schematized this way. You have two kinds of hopping amplitudes between the unit cell. The unit cell is this compound of carbon and hydrogen, and depending on, you move from left to the left or to the right, you have different tunneling amplitudes. So you can describe the system this way. You have two amplitudes, T1 and T2, and let's say the species is the same. A is the same than B, but they are connected in this staggered way. So if you want, you write the Hamiltonian of the system, can be this form. This is a second quantization Hamiltonian. You have an excitation that can jump within a cell, and is the cell index with amplitude T1, or between nearest neighbor cells with a different amplitude, which is T2. This Hamiltonian can be easily diagonalized by introducing two different Fourier transforms for the two different sublattices. There's this form, and you get something that is diagonal in the momentum space, in the reciprocal lattice space. And the form of this Hamiltonian is a 2x2 matrix, this way, when you have this only non-diagonal elements. you you calculate the eigenvalues of this matrix, and you find the band structure of the model, which has this form. For if T1 is different from T2, you get this two-band structure with a gap within the two bands. Only in the case T1 equal to 2, the gap closes, and you have a continuum band, only one. This is in the Bravais lattice representation, of course. Where is topology in this model? The simplest way to see the appearance of topology is to consider, instead of considering a closed chain, you consider an open chain. So you have something that has two endpoints and sides of the chain. If you do it, you see that there are two different phases. In one of the phases, when T1 is smaller than T2, if the number of sides is big enough, you essentially find the very same two-band structure of the original model. You don't see any difference. In the other phase, you find two that generate eigenvalues here in the middle of the band, with energy that is exactly 0. If you calculate the eigenvectors corresponding to these localized eigenvalues, it's just an edge state. You have this stage at one end of the chain, and you have another state analogous at the other end. And the other strange things about this state is that it occupies only one of the two sublattices. Let's say B, 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 but you have amplitude probability 0 over all the A sides, and the other way around for the other edge state.
Sorry for interrupting, somehow technical question. You were mentioning when you have the closed chain,
Yeah.
that then, so when you diagonalize, you apply these
Yes.
transforms and so on. But this closed chain, you have a circular matrix. In the open chains, the matrix is not always circular.
Yes, yeah.
Are you able to do the same procedure?
To diagonalize it, yes. Actually, here I wrote.
But not in the same way, right?
I wrote key, and key is actually a number which is 2 pi divided by the total number of cells, 2 pi divided by n, where n is the total number of cells. If you use the open chain, you have to diagonalize it putting n plus 1 in the denominator instead of n, and then you have to take combinations of modes. You have to do a sine Fourier transform, let's say that, instead of
You have to write all the conditions.
you? Open boundary conditions. You impose that at the ends the wave function is 0. So you have to you find the sine Fourier transform. Yeah.
I don't know if it is related, but a simple question. Do you have a simple analog of a classical topological transition?
I don't know any of them. I don't know.
Define classical topology, maybe you can speak about it.
Classical means that you don't need to start with a quantum Hamiltonian. Classical, non-quantum.
This can be harmonic oscillator, and this can be modes of light, and then you write a classical Hamiltonian.
What would be the transition?
The design that is same.
The same waves, H waves,
Yes.
using the coordinates.
Instead of the wave function, you use the electromagnetic field.
Yeah, the vibration of those classical oscillators only on the even oscillators and not on the odd ones, and concentrated mainly in the borders. I mean, this
So
could be
there
a
is-
chain of oscillators, no?
So there is nothing especially quantum in the concept of topological transition.
The
Try to start from, not higher, but from the beginning.
I don't know if everybody would agree, but I would say that at this level, not necessarily. You can do it also with higher level, also only when in the state and with this basic level, you can do it also with classical light.
With classical amplitude.
Maybe the discreteness of the states. These
Yeah.
states are discrete.
One
State.
This is the simplest case. There are
I'm asking-
the quantum hole is different from the Hall effect, for instance. You have something much more in the quantum description of the Hall effect.
So that's why I'm asking what
Yeah.
would be the simplest example of a topological transition in classical physics if this exists.
Well, it's only in optics. Certainly, I don't remember all the details, but in nonlinear optics, you have these things too.
And
Classical
those,
optics.
and those are called topological transitions.
They are called topological transitions. Actually, that's why Stefan alone we know about this.
Of course.
Yeah. Yeah.
Okay.
But I think in this case you need quantumness to describe 2D, because you have quantized levels, you have to jump from one level to another one. I don't know if there is something.
Yeah, no.
I mean, if you're talking of, I don't know, some DNA chain or whatever,
Yeah.
that it is open or it is in a modular band, this transition should be possible to be described classically. I guess, I don't know.
But it's all geometrical,
Yeah.
isn't it?
It's a geometrical
It's
effect, yes.
it's a geometrical construction,
Yeah.
so you can build whatever you want, and you can call it a phase transition in this sense. I mean, this is just because it's about the structure of the eigenvectors of and for that reason it's quantum. But yeah, I wouldn't say this is a quantum phase transition as we call the quantum phase transition of the Ising model with respect to the classical phase transition.
But this is another kind.
It's totally
Yeah,
different,
yeah.
No,
right?
no, actually,
Yeah,
there is no
it's-
claim of this.
Exactly, it's totally different. This one is simply geometrical.
We didn't write it's a quantum topological, it's just a topological.
Yeah.
It's a topological transition in a
Yeah,
quantum
but
system.
Yes.
So this state is here, and the strange, yeah, Damian.
Yeah, so it's a linear. So that's a linear.
It is a quadratic Hamiltonian and linear dynamics.
Yes.
Yeah.
When the dynamics is linear, the topology is quadratic. So it's a linear model.
Linear.
Yes.
It's not only localization.
No, it is linear. Yeah. So you find this value, and the strange thing is that you keep having these exactly eigenvalues, couple of eigenvalues here. Also, if you deform the chain, instead of having a perfectly staggered T2, T1, T2, T1, you add some noise at this value. If the noise is not too high, you still have this edge state. Of course, the amplitudes slightly change, but you can still solve analytically. You can calculate analytically the form of the shape, the form of the state. So why is there a state in one phase and not in the other one? A simple way of seeing it is taking the fully dimerized limit, where either T1 is 0 or T2 is 0. In one case, you get dimers arranged this way, and that define two flat bands, just two energy levels, one positive, the other negative. In the other case, you have the same band with the energy plus or minus T1, but then you have two isolated extreme sites that define your edge states with zero energy. So you can, more formally, you can understand why there is this, why the states are protected outside this full dimerized limit, is because there exists a symmetry called the chiral symmetry in the Hamiltonian that also holds if you deform.
Yeah. Sorry, in the full array,
Yeah.
it is necessary always that the end edges are the T2. I mean, because the way you plot it there, that in the full array was array with all the edges, all the connections.
Yeah.
The ones on the stream are T2. But you could have, I guess, an array with the
But
outer.
well, I am assuming that the number of sites is even. This is fundamental. If not, you have some frustration.
But would you have even sides and just interchange, because that there is.
But if you interchange, yeah.
I mean,
No. Here you don't have any case in which there are three T2s and two single elements not connected. Can you change T1 by T2? Can you have?
But if you change T1 by T2, you just change the phase.
No, because the T2 So it's in the original change, T2 is a connection which is stronger than T1 or whatever.
No, it can be either stronger or
The
weaker.
first line, T2 is stronger. In the second line, T2 is weaker.
It's actually 0 in the second line.
You change the role and you change the weakness, it's a symmetry of the problem.
So what are the lines in
All the cases are contained there. There are no more cases in the case of
If you define T1 as the center of the chain, let's say that, at the center link.
It doesn't really matter like this. It's just a notation that you have for the whole line.
I fixed T1 as the central link of the chain, then everyone is,
Then, but yeah, instead of the whole line, it would be just blue and yellow.
yeah. So this is just a mathematical aspect. The state is protected by this chiral symmetry, because if you deform the Hamiltonian, it still anti-commutes with the Hamiltonian, and you can show that it is necessary to have a state with 0 energy. Just to resume, then, an open chain, T1 less than T2, no edge states. T1 greater than T2, you have edge states. This is an open chain characterization. Actually, there is a totally equivalent other characterization you can do without looking at the boundaries, looking at the bulk of the chain. And it's called the edge bulk correspondence. Actually, if you go back to the K Hamiltonian, if you remember before I wrote this formula, and if I introduce the polymatrices sigma x and sigma y, I can rewrite this 2 by 2 Hamiltonian in this way. It's just a sum of a part parallel, let's say, the parallel to sigma x and another part parallel to sigma y. If I try to plot this line in a plane where sigma x is the x-axis and sigma y is the y-axis, I get something like this. In one case, I have a circle. This is just the amplitude of the modulus of this vector, let's say that. A circle that winds around the origin of the axis. And in the other case, the circle does not wind around the origin. So this allows one to define a topological number, which is called a winding number, or also Zach phase, as the number of times that the loops wind around the origin of this sigma x, sigma y plane. And it is exactly equal to the number of edge state for each of the edges. And this is a general property. It's not only a property of this model, but this is a property of all known topological systems. So in one case, I have W, the winding number is 1, in the other case is 0. And there is a total correspondence between this number and this feature here and here. No edge state, the W is 0, edge states, W is the number of edge states, 1. So this has been widely exploited, this correspondence has been widely exploited to study actually, so in order to find which is the value of this number, you can just count the number of edge states. So you exploit the bulk edge correspondence to determine the bulk topological numbers by counting the number of edge states. And it has been done in different platforms with cold atoms, with in a photonic array, with small Rieberg atoms, and other similar stuff, let's say. But there is another way of measuring bulk topology, which is also very popular. And it is based on a dynamical process. Let's say you prepare some initial state in the middle of the chain. You let this state evolve according to some rules. You do some operations at a given time, and you let it evolve. And then, depending on the phase you are, you get two very different distribution probabilities around the chain that you can detect. Of course, you measure, you repeat the experiment many times. You measure the probability of finding the excitation in one of the sites. You reconstruct the profile of the distribution. And from this profile of distribution, you can distinguish if you are in one phase or in the other one, because they evolve with different velocities, let's say that. And these two methods are the two methods that are normally employed in a lot of experiments to measure these topological numbers. What we propose is a bit different. And here there is a series of recent experiments about this technique. We propose something different. We propose to measure locally, in the bulk, the topological number with a local measure. In this case, either you go to the edges or you do a spatially distributed measure extended all over the chain. We propose that if you add some external object to the chain, you can, only observing the behavior of this object, measure the same numbers. This is our idea. So before doing that, I have to define something about open quantum systems. You have a small system immersed in a large environment. If you want to calculate the dynamics of the small system, you take the total Hamiltonian, which is system, bath, and interaction between system and bath. You let the initial state evolve, and then you trace out the degrees of freedom of the environment. And this is the evolution of the system, small system density matrix. Essentially, we can divide the kinds of evolution into two categories, Markovian or non-Markovian. In Markovian dynamics, there is negligible correlation between system and bath at all times, and the dynamics of the system is memoryless. On the other hand, if you have some kind of non-Markovianity, it means that there are correlations created during the dynamics between the system and the bath, and there is a blood flow of information from the bath to the system that makes memory effects not negligible. More formally, a Markovian, if I have an initial state, rho s of t, rho of 0, and at the time t it evolves according to a map phi of t, if this map is Markovian, it must obey this property, which is the semi-group property. The map at time t1 plus t2 is just the product of the two maps. And another thing I have to define is the distance between two states. Given two states, rho 1 and 2, I can define the trace distance between them as the trace of the absolute value of the difference between them. And this is a valid way of characterize the distinguishability between states. If the distance is 0, it means that you have the same state. If the distance is maximum, they are orthogonal in a way. Because of this of semi-group properties, this map, in the case of the Markovian map, this distance is contractive. It means that if you take the distance at the initial time and you let the states evolve according to a Markovian map, this distance must decrease. So the map diminishes the distance between the two states. And this can be exploited to define a measure of non-Markovianity. In fact, if you define the rate of change of the distance as the time derivative, given to states 1 and 2, if the evolution is Markovian, this must decrease in time. So this must be negative. If you have some time windows where this quantity is positive, it means that there is no Markovianity in the evolution. So you can define the amount of non-Markovianity of a map just taking all possible states, initial state, rho 1 or rho 2 of your Hilbert space, and then you take the integral of this rate only in the time windows where it is increasing. Because in those time windows, you are detecting non-Markovianity. This is a definition that was given 10 years ago. There are in the literature 3 or 4 different definitions, but more or less they are very similar. They all play with this kind of contractingness. And so we use this measure to characterize our dynamics.
So sorry, the maximization is over the initial conditions?
Over all the possible pairs of initial conditions. Actually, in the case we have studied, we are lucky because we don't need to do this optimization, which is in general a big problem. If the evolution of rho is not so strange, you find a way to optimize it. So this is actually our model. We have a Su-Schrieffer-Heeger chain, and the probe, the external probe, is a two-level system with 2 levels, excited and ground state, connected to one elementary cell. Of course, you cannot connect this probe to one site, because otherwise it would be impossible to distinguish between the two phases. The problem would be invariant under the exchange T1 and T2. This is the minimum amount of interaction you need to have to observe something, depending on the topology. So we have the system, the bath, the probe, and the interaction. The probe, the probe, you can just take a two-level system with difference of energy, omega 0, and then we studied two possible kinds of interaction. The phasing interaction, where you don't have any exchange of energy between probe, of excitation between probe and chain, and the other case it's a dissipation process, where you can destroy a particle here and create one here, or vice versa. Why is it called dephasing? Because, so let me start with this case. This case is called dephasing because if you take as initial, whatever initial state with some coherence for the probe and whatever initial state for the bath, the state of the probe evolves according to this rule. The populations are constant in time, while the coherences are affected by this decoherence factor. It's called dephasing because you have pure dephasing. You don't have any kind of exchange of population between the two levels. So this is, the dynamics is all here in these factors. And these factors can be calculated as the average value of the initial state of the bath. On the right hand, you evolve it according to a dressed Hamiltonian. On the left hand, you have just the bare SSH chain. The dressed Hamiltonian is the original Hamiltonian plus a local defect, a local cell potential. And just to mention that this Q, the modulus, the square of the modulus of this Q is known in literature as the Loschmidt-Echo. And it measures the way you take an initial state, you let it evolve according to different dynamics, and you study the distance as a function of time. It is known as Loschmidt-Echo. So if you want to solve this problem, you need to study the characteristics of this Hamiltonian. And this is what we did. We studied the eigenvalues, and we found that if the number of sites is big enough, you still have the two bands that you had in the original model without defect, plus some levels that are outside the band. And these levels are actually bound states localized around the impurity. We calculated it just assuming that they scale exponentially around the impurity, and we found an analytical expression for their energies and their symmetry. Because the important thing here is that those states can be either symmetric around the center of the chain, or antisymmetric. So these antisymmetric states are here, and here, and here, and here. If you look at this picture, you know that in one of the phases, you always have two black states, symmetric states, and here you have only have one. Here you have either 0 or 2 red states. Here you always have 1. So this is just a topological number for this dressed model, because you can define a topological number nu as -1 to the number of antisymmetric states or the number of symmetric states, which is equal. And you find that here you have +1 and here you have -1. So this is a new way of characterizing the phase of this dressed Hamiltonian. Here we are plotting the energy spectrum as a function of the coupling. We can look at the same from a different perspective. Instead of, here we fixed actually the coupling, and we changed the ratio between T1 and T2. And this is interesting because here we can analyze what happens around the topological phase transition, T1 equal to T2. Because here around, on the left side, you always have two symmetric states. On the right side, you have one symmetric state and another one which is antisymmetric. So it means that if you choose as an initial state, a state that has a given symmetry, when you transitate here around the phase transition, you can observe a very big change in the dynamics of this state because it will be blind to one symmetry and it will be only sensitive to the other one. So if the initial state has a given symmetry, it will only see the bound states that have the same symmetry because the other one are orthogonal.
So where is in this plot the intensity of the coupling to this external map?
Actually, it is fixed, but it is two times this point.
So how does it affect? So if you if you couple very weakly to the map, it should be the three case. But is this the case?
Well, these red lines intercept this axis here. Let's say that. So you reduce the space of this window.
Can you repeat symmetry or anti-symmetry in what sense? In space inversion?
Well, I can show something that I have here, for instance. This is an example. This is an antisymmetric state. This is the center of the chain. And the wave function is this way. 1/2, minus 1/2, minus 1/2, 1/2. It's a spatial symmetry. If a symmetric state, it would be plus 1/2, plus 1/2.
And also in energy space, the inversion energy symmetry is lost also.
This is not an eigenstate of the Hamiltonian. You mean these are
the color bars? They are symmetric around 0. But these other states, at some point, you lose the symmetry.
what do you? This disappears here. It enters in the band. Let's say that you have
Like changing sign of the particle hole impression. This is broken.
This is broken here, for instance. Yeah. Not here, but here it is, of course. Okay. So depending on the initial state, you can see the number of bound states you want to see, let's say that. And because of this, you can have two very different dynamics. For instance, this is an antisymmetric initial state, which can be written this way. And if you study the dynamics of these states, at this state you find something like this. In one of the phases, you have a strong oscillation. In the other one, apart from some initial dynamics, you have a steady state. And this oscillation is just the interaction of the initial state, the bouncing between the initial state and the bound state with the same symmetry. As the initial state is antisymmetric, it only sees in the dynamics this state. Here you don't have any effective bound state. Here you have one. So you have a behavior that is strongly oscillating or not. So the oscillations of this quantity have something to do with non-Markovianity. Of course, they have to do with this. If you apply this measure of non-Markovianity to our evolution of the matrix, you discover that the non-Markovianity is just the integral of the Loschmidt-Echo, of the square root of the Loschmidt-Echo calculated in the time windows where the Loschmidt-Echo is increasing. So you have to take all this increasing part, you sum them, you take this function, so the difference between this function here and here, here and here, and so on and so forth. And this is the amount of non-Markovianity of your dynamics. In the other case, it is almost 0. So this is a highly non-Markovian behavior. This is a mostly Markovian behavior. Actually, as we have oscillations, this non-Markovianity will diverge at a given point, but the measure can be normalized by introducing a maximum t, and then integrating from 0 to t and normalizing by the total time. So we measure the non-Markovianity for different values of the coupling, and we found this kind of behavior. Around the critical point, here you have almost 0, and here you have a macroscopic value for non-Markovianity. And in a way, we have equipped a topological phase transition with a classical order parameter. Topological phase transitions are known not to have any order parameter in the Landau sense. Here we have found something that is not exactly that, but is very similar to the behavior of an order parameter for the phase transition. So this phase transition is something that is more quantum in the sense that the Ising model Marco was mentioning before.
But it's a bizarre way of the parameter, no? When you go close to the critical point, the slope changes with the parameter.
With the coupling, yes.
Well, it's typically the critical exponent does not depend on.
Yeah, this is not exactly that kind of phase transition. But
No es una cosa muy pero la pendiente cambia. Parece que se aproxima linealmente con una pendiente que cambia.
But we actually don't know if there are some scaling laws or not.
Bueno, no, la de gamma 1.2 es más parabólica. No, la de 1.2 es muy lineal.
Sí. Es igual. Igual no es, o sea que...
Okay, so this is the first kind of interaction. We also studied, as I said before, the case of this dissipative dynamics, where we can exchange interaction between system and probe. And this is dissipative because now if you assign initial values to the density matrix of the probe, EE, GGE, and GG, the dynamics is this way, so you have loss of coherence, but you also have changes in the population. And this is a dissipation because this interaction is for long time. Let's say you find the system in the ground state 0, 0, 0, 1. So we also studied the bound state diagram for this case, and what we found is that here there is no dependence on the symmetry. All the states, the bound states, are symmetric with respect to the center of the chain, but nevertheless, we can have a dependence on the number of bound states. For instance, if you take the same value of the coupling here, gamma equal to 2, here we have 3 bound states, here we have 1. So we don't have a direct tool like before to inspect the difference between the two phases, but still, for instance, we studied the dynamics in the two cases. We found this kind. Here you can study the spectrum of the dynamics in the two cases, and from the spectrum you can count the number of bound states, and from this number detect the topology. It's a two-step process, but it's still effective. Actually, there is a special case when gamma is equal to 1, where you have something very similar to what we have seen in the other model, and in this case you can measure non-Markovianity. Also, it is an effective measure. Of course, here, non-Markovianity does not distinguish between the two dynamics. It's you don't expect to finding a sensitivity of that measure to the change of phase. In this case, this special case, of course, it is different because it is 0 here, and it is not 0, it's macroscopic here. So you have something like this. The difference between these two changes is that here it's a kind of first order phase transition. In the other case it's just similar, it's not the same, but to a second order phase transition with the discontinuity of this fake order parameter here.
This is the first order.
Oh, sorry, yeah, okay. So this is the end of the presentation. We have proposed a protocol for purely local detection of topological quantum numbers of the Su-Schrieffer-Heeger Su-Schrieffer-Heeger chain, considering different kinds of system-bus interaction. And we have shown that non-Markovianity can be a useful tool in order to characterize topological numbers. Of course, this is a simple model. We hope that we can apply it to systems with more than 2 numbers to see if it's still possible to find something that is useful in different experimental platforms. So, thank you for your attention.
So we have some time for comments or questions.
What's the difference of the topological edge states of this work with the ones of a Majorana-Arrhenian?
Of course, this where is this? This is actually very similar to the structure of the Kitaev model. Yes, it is.
But is there any fundamental difference between this and the Majorana-Arrhenian topological edge states?
When you mean fundamental?
Well, if it's
Fundamental between boson and fermions?
for example, I don't know. These are bosons.
Well, this can be either bosons or fermions, actually.
In one state?
Yeah.
Okay.
I have a question myself. I'm a bit confused by the message of your result. If I understand well, your finding is that the probe is also affecting the topological phase of the system.
No.
It depends on this parameter gamma.
No, it is not actually, because you can define these two. You have those 2 topological numbers that are 1 and 0 for the 2 phases, and you find the same binary structure here. Only this is +1 and this is -1, because you count the number of states, the parity of the number of edge states, of bound states.
So in this sense, the probe is not affecting the topological.
No, the problem just wants to recover this number. You want to observe this number by only measuring the probe.
But you have large differences in the spectrum, no? Depending on gamma.
Yes?
Depending on the gamma.
Yeah.
So my question was, isn't it somehow in contradiction with this idea of robustness of the topological phase?
But this is totally robust because you can choose whatever value and that number does not change.
But the spectrum itself changes.
Yes, this is not a state that is fixed like the edge state of the Baire model, SSH model. But the duality is that here there is, I mean, this is a bulk measure, it's not an edge measure. Here you have something similar, let's say that these figures depend on the parameters.
So in this sense, the probe is not affected.
The number is a phase number. You have a number in a phase and another number in another phase.
Gianluca, beyond the mathematics, do you have any physical intuition of the connection between topology and non-Markovianity?
Yes. So the point is that depending on the we have used non-Markovianity. You could think about other kind of quantifiers. But the point is that you have topology who have a fundamental difference in the spectrum of your system, and you exploit this difference to measure something. Here the difference is in the symmetry of the states, and we thought that we could exploit the symmetry of the states to design a protocol that is symmetry dependent. Non-Markovianity is just something that is sensitive to this property. So there is something in the middle. It's symmetry in the middle between topology.
But why memory has to do with symmetry?
It's not that memory has to do the symmetry. You can, there are selection rules in your problem, and you exploit these rules to be something that is symmetry dependent. It's not a universal protocol, of course.
No, but I'm trying to understand. To me, non-Markovianity is memory effect.
Yes.
And what is the physical relation?
You have memory effect because you have a localized state and you bounce between your state and this localized state.
When this is created, you have continuity bouncing of information, while when it's not created, the information just flow back.
There is just a band and you decay.
It's like having two half chains if the coupling in the middle is long. While in the other case, you have like a triangle. So that's the intuition.
Okay, I missed that.
I have a question. You in this expression, in this figure here, that's the center state of the chain.
Yeah.
But I understand that you don't need to put when you do the proof, you don't need to do the proof on the central side of the chain.
But
you can do it anyway.
yes, but then you choose the point and that fixes. This is a closed chain. We do the protocol with the closed chain. So you
do the protocol not in a ring.
No, with a ring.
No, but then
So you fix the
ring there are no H states.
No, there is not. No, there is these bound states that are not the same thing.
No, I'm saying,
Yeah.
when you try to prove, when you do the measurement on the chain, you are going to do the measurement where the system is in one state of the other.
One phase or the other phase.
Yeah,
Yes.
but that's an open chain.
No.
But the two phases are present also in the closed chain. You have this
I mean, this bound state, this edge state correspond to these two different phases also in the
You
bulk.
can test that on the closed chain and see what, okay, and then if that's the case, that means that if this chain is open, you have the two states. Okay.
This is a
So
correspondence.
you test on
Yeah.
the closed chain.
Yes.
Okay.
So you fix the center of the chain.
Actually, if you look at it a short time, if you take a chain that is long enough for not having information bouncing back into the center of the system, you could do the same on an open chain.
Yeah, no, but I missed the point that you were testing the closed chain. I thought that you were testing the open chain.
More questions? If not, let's thank Gianluca again.
Pero entonces cuando tienes es una open chain.
Pero, espera.